Okay, in this video, we're going to do one more example of induction. This time we're going to prove something about um, dividing. So here's the example I want to prove by induction. So we want to show that 5 always divides 6 to the power n minus 1, where n is any natural number. Okay, so let's do a proof sketch just to play around here. So we're going to assume we'll make the strong inductive hypothesis. So we're going to assume that it does work. So what does it mean for 5 to divide? That means that 6 to the n minus 1 can be written as some multiple of 5, right? So for some k in the natural numbers. That's what it means for 5 to divide something, right? So it can be written as 5 times something. Okay, so let's see. Now we have to look at 6 to the power n plus 1 minus 1. All right, well, now we're going to do this. This trick that I'm about to do is something that gets used a lot in mathematics. It's where we sort of add a fancy zero, if you will. So I'm going to subtract 6 to the power n, and I'm going to add, I'm going to add 6 to the power m. And I just want to point out that, notice I've given myself something to work with, but this is just equal to 0. So I haven't actually changed the formula at all. But I've introduced in the second piece, right, the second half, I've introduced something which is the inductive hypothesis, right? So that's helpful. And on the other side, I can try to, work out something on the other side, right? So we have to make this work now, but it's helpful because I've introduced the inductive hypothesis. So the reason why you might think to do this is because you're trying to make the inductive hypothesis show up. And when you first look at the formula, there's no reason to see that it would, right? So now in the first grouping, 6 to the n plus 1 minus 6 to the n, of course, there's a common power of 6 to the n. So I'm going to pull that out. So that would leave me 1, 6, and no 6's. So that's 6 minus 1. And the second part is just the inductive hypothesis. So I'll just rewrite it for a second just to see what's going on. Okay, but now what do we have? So the first one can be written as 6 to the n times 5. Well, that's beautiful. And the second one, by inductive hypothesis, can be written as 5 times k. Okay, but now there's a 5 that, of course, I want to pull out. So I get 6 to the power n plus k. And now I don't really care about what's in the parentheses because what's important is that it's multiplied by 5. And so that means the entire thing is divisible by 5, and that's what we were trying to show. So that's the end of the sketch. Let's go into the proof since now we understand how this should go. Okay, so we will proceed by induction. Now, notice it seemed like we might need strong induction here, but really we kind of used the base case here. So we used the inductive hypothesis and we used the base case sort of, right? We don't really even need to think about it as the base case per se. It's just that we get to find a 5. And so we don't actually need to use any other, we don't need strong induction here actually. So what is the base case though? We haven't actually checked it yet. So the base case for this formula is when n is equal to 1, and we just need to check that 6 to the power 1 minus 1, which is equal to 5. And of course, it's kind of silly to write it like this, but just to be clear, that's 5 times something, so it's divisible by 5. Perfect. So now let's go to the inductive case. Okay, so now we assume that 5 divides 6 to the power n minus 1. Let me just give myself some room here. And we will show that 5 divides 6 to the n plus 1 minus 1. Okay, so by definition, uh, 5 divides 6 to the n minus 1 implies that there exists a k, a natural number, so that 6 to the power n minus 1 is equal to 5 times k. Now consider, so now we do the calculation we took ourselves through before in the sketch. So we take, again, now we want to subtract 6 to the power n and add it. And again, the motivation here was to introduce the inductive hypothesis on the right and then hope to be able to deal with the rest, which we already know works. So in the first grouping, we pull out the 6 to the n. And the second grouping is beautiful. And now we see that this is 6 to the n times 5 plus, using the inductive hypothesis, 5 times k. And we just pull out the 5. And now let's just point out to the reader that, hence, let's put it into the dividing notation now. So that means that 5 divides 6 to the n plus 1 power minus 1. Beautiful. And so by induction, we see that 5 divides 6 to the n minus 1 for all n in the natural numbers. Perfect, which is what we were trying to prove. Great. Again, notice we didn't actually need the strong inductive hypothesis, because when we broke it down into two pieces here in this step, it turns out that one of them is the inductive hypothesis, not the strong inductive hypothesis. And the other one basically just gives us a 5 to divide by things, and which is sort of the base case in the parentheses. And we don't really need the inductive hypothesis for that. It just kind of falls out and gives us a 5. So that's perfectly fine.